Hi folks, so in this video what we're going to do is complete the 2013 higher level Section A questions from the DCG exam. There's 4 questions on the paper as always in Section A and you have to do 3 of them. So what I'm going to do is just work through them from A1, A2, A3 and A4. So starting off there, I'm just going to zoom in there onto the A1 question. Right, so just setting it up there. So it says here for question number A1, it's the 3D graphic below shows Rubik's Cube and the display stand. The drawing on the right shows the incomplete projections of the objects. Part A, complete the elevation of the cube, which is in here. And part B, it is planned to package the cube without the stand in a plastic sphere. Determine the diameter of the smallest possible sphere that will contain the cube and draw the sphere in the end view. Okay, so we'll get on to part B after we do part A. So what we have to do here, we're given the plan view and we're given the end elevation view over here, or sometimes that's called the end view, and we have to complete the elevation view of the cube. Okay, and essentially the elevation view of the cube will actually show us this green face here, the white face and the red face. Now, easiest way to do this is actually just plot the points, okay? So I'm going to use a little bit of labeling here to help me determine how I'm going to draw it here in the elevation. If we take a cube, there's actually technically only 8 vertices on it, okay? If we take the green surface at the bottom, there would be 1, 2, there'll be 1 inside here, 3 and 4, and there'll be another 4 at the top. So I'm going to label those. I'm going to label the ones at the front with maybe A, B, C, and D, and the ones at the back maybe 1, 2, 3, 4, or I could do E, F, G, and H. So the very top point here, I'm going to call this A. Just going to label that there, just with the letter A. Then here, I'm going to say B. Then as this goes down, there'll be C there, and then it will come back to D. So we'll go A, B, C, D. Okay, now if I was to label that in this view, the highest point, technically, would be this one here. Now, I'm focusing on this face here. So that's actually this face. I'm only seeing the top 2 edges, and then the other 2 are going to be in hidden detail in the plan view. So I can only see these 2. I can't see the edge running from B to C. So this one here would be A. Then I'm going to call this one out here B. C is going to be all the way down here, inside there, and then we have D out here. So A, B, C, and D. I'm going to do the exact same here on the back surface. I'm going to say E, I'm going to say F, then it goes to G, and then it will be H. Okay, so E, F, G, and H. The top point, okay, is this one here, and C is on the ground. It looks like they're sharing the same place. They share the same relationship in the sense that they're in the same position on the sheet, but technically C we know is actually on the ground, whereas E, I'm going to put it in here as well, is on the top. So it goes E out to F, and then it's going to go to G here at the back, and then we have H. Okay, so there's my points, and now all I'm going to do is I'm going to plot those. So normal orthographic rules apply. So I'm going to project up, only 3 lines to project upwards. So that line there, that will go up to the elevation. Then this one on the outside, and likewise with this one here. Okay, so I've projected those up. Now I'm going to project them across. C's already gone across, so very handy there. Those 2 are in line with each other. Those 2 are in line with each other. And that. Okay, now if I want to find those points, as I look at the object, technically for the elevation, it's like we're looking in at this face here. So I will see the face A, B, C, D. I will actually see that face. So that's the first face I'm actually going to look for. Now the edge B to C and the edge D down to C does get a cut off, and it'll probably get cut off right here. You can see in these points down here. They give us the kind of graphic here to give us a little hand. So I'm going to plot those points now. So if I wanted to find A, is up along here and where A comes across. So that's my A there. And now if I want to find B, there's B. If I want to find C, C is down here and C is across, so there's C. And then if I want to find D, there's D. Okay, let's connect those up. So A to B to C to D. Just sharpen the pencils. And there's that. Now, depending on my accuracy, more than likely, as I said, it should go through there. It does in this case. Put it down there. There we go. So that'll connect to there and to there. Now, technically, I can see the edge from A to B. I can also see this bit of it. But inside here, I should have gone a little bit dark there. So I'm just going to use my rubber. Go a little bit lighter. Inside here should be hidden detail. Okay? Because as the cube goes into the stand, we're not going to see that edge the whole way. There's the first face. Okay, now I'm going to see the next face here, the white face on the outside, okay, which is technically the surface going from A, B, F, and E. So you'll see it here, A, B, F, and E. So, if I was to find those as well and plot those points, I'm going to find F now next. So F is up here and it's out here, so there's F. And E is up here, follow it across, there's E. And last one then will be H, which is going to be out here. And then I also have, so E, F, and I want to find G as well. G is coming from there and out here, and there's G. And once again, going to probably have a little bit of hidden detail. So I'm going to draw my lines first. So E connects to F like that. Likewise with the H. And F down to G. And H to G. Okay, heaving in the right parts now. Just going to heavy in the faces that I can see. So as I look at it in this direction, just making sure, yeah, I can see the face here. So I can heavy in that face. So all those faces can go in heavy. Heavy in this face. That face there, okay? And that's like the cube as I look at it. Now, there's obviously faces that are running at the back of it. So from F to G, that edge there is at the back of it. As I'm looking in this direction, I can't see the F to G line. So I would obviously have to put that in as hidden detail. It's going to be the exact same with this one here. And then there's also an edge connecting from G to C. 6 faces on the cube. There we go. Okay, so there we have it. That's the first part of the question completed. Complete the elevation. Okay, now part B, it is planned to package the cube without the stand. So we're removing the Rubik's stand here, okay, in a plastic sphere. Determine the diameter of the smallest possible sphere that will contain the cube and draw that sphere in the end view. Okay, so important information there. They tell us they want us to do it in the end view over here, or sometimes that's called the end elevation. So what we're going to do is we need to get the smallest possible sphere that will contain this cube, okay? And you can see we've got the large rectangle here, but really what we're actually looking for is just the longest diagonal, okay? And the longest diagonal in this case, as we see it in the end view, is actually going to be the diagonal connecting from E down to C. Now that actually should appear, that should appear in a vertical line, and it does. So if I draw that line in, okay, and I draw that line in, technically, if I was to connect the other diagonal from A to G, that should split it right in the middle there. Okay, I could bisect it as well, but technically that point right there is my center point. And now with that as my center point, what I want to do is I'm going to take the distance from the center point to the E point up here as my radius. Now I'll always just check it first. See that it encompasses all the points. So there's that one, through that one, goes through A, and goes through C as well. And draw that in as best I can. There's that side done. Just want to make sure I'm neat and accurate as well. There we go. Okay, there you have it, guys. That there is the smallest possible sphere that will contain the Rubik's Cube when the stand has been removed. Okay, so all I did was I found the longest diagonal. Okay, I could have bisected it, but technically when I joined the diagonal from A to G as well, that will also then give me the center point. So I use that, and then I use the radius from here to here. So technically that's the radius distance that I need. Okay, that there is the first question, guys, an orthographic question. This bit, not too bad. It's just a case of obviously deciphering which surfaces need to be heavy and so on. Whereas this bit here might catch out a few students, but it was easy enough if you have good understanding about it. Right, question A2. So we're going to come down to this one here now. And this question here revolves, or encompasses the area of solids in contact. So it says here, the graphic below shows a bowling ball and pins. We can see obviously the bowling ball, and we've got one pin here. Drawing on the right shows the elevation and incomplete plan of one of the pins and the bowling ball in contact with each other. Part A, complete the plan of the solids in contact. Okay, so we've obviously got the pin here, and there's the bird's eye view of the pin, and we have to get the bowling ball in position down here. Okay, and we're going to have to find then points of contact and things like that. Now, technically, if the center of the bowling ball in elevation is right here, it has to be directly below it in plan. Now, this actually relates a lot to junior cert graphics. So technically, my center point has to be somewhere down along there. Now, the only way I can actually find it, technically, is by getting the radius up here. I'm going to mark it out, and I'm going to bring this bowling ball. Imagine it was rolled around until it was in contact at the side of it. Okay, so I'm going to extend out the axis line here from the pin. Okay, and I'm extending that out. And what I'm going to do now is I'm going to get a compass. I'm going to take the radius of the bowling ball. So I'm going to take that distance there on my compass, from there to there, and I'm going to mark it out from the side of the pin. And imagine, I'm going to draw it in. Technically, all I've done is I've moved the center from here out. And imagine now we've moved the bowling ball. I'm just going to draw it in lightly. It's like we've taken the bowling ball. Okay, you can see it in there very lightly. It's like I've taken the bowling ball and I've rotated it around the object until it's in contact with technically the extreme edge of the bowling pin. Okay, so now it's in contact right here, right around there. Okay, now that I've found a new center, okay, that's often called getting a ghost sphere, I can bring that down and use that center from this position right here. Okay, now that's not the bowling ball when it's in its correct position, but that's when I've taken the bowling ball and I've rotated it back until it was in this position at the side of it. Okay, but what's helpful about that is now that I have it here, as that center as the bowling ball will be in contact with the pin as it rotates around it, so would the center rotate as well. So from the center of the pin, I will then rotate the center. Okay, and I've rotated the center until it's in its correct position right here. And now, go back up, get the radius, because any sphere will just be a circle in any view, and then draw that in. There we go. Okay, so there is our bowling ball drawn in our plan view, and usually in these questions they often ask you to get the points of contact. So technically if you connect the two center points, okay, my point of contact will be right in there. I'm going to write POC, and the other point of contact in the elevation then, once I've found in plan, I can then project it up to the elevation. And the points of contact will be where the center line is in line with the center line of this one. So there it is. That's my point of contact there. Okay, inside there. Right, so that's the first part of the question. Complete the plan of the solids in contact. We've done that. Now what we have to do, it says here, draw the plan. So we just have to draw the plan. I might do the elevation, we'll see in a second. So I have to draw the plan of a right cylinder. What that basically means is, which draw the plan of a cylinder that is standing upright, okay, which stands upright on the horizontal plane. The top of the cylinder touches the pin at the point P and also touches the ball. Okay, so you can see here we've got point P in elevation and we've also got that point P in the plan. And the top of the cylinder is touching that. So one thing I know straight away then, in this case, is in my plan view, from the center, through point P, if I was to extend that out, somewhere out along that line is going to be the center point of my cylinder. Okay, somewhere out along that line, because it has to be in contact with it at point P. Okay, just make sure I've got that through point P properly. Apologies there, guys, just going to rub that out. I want to make sure my accuracy is correct. From the center. There we go. Okay, now somewhere along that line is going to be the center point of my cylinder. So, to get that, what I'm going to have to do is I'm going to have to find a point somewhere on that center line that is equidistant away from the pin and the bowling ball. Okay, and the only way I can actually do that is by using something called loci, okay, or a locus of a point. So what I'm going to do is, from the side of the pin, I'm going to extend the line out, and I'm also going to extend a line out from, I'm just thinking here, I'll come out at this angle. Doesn't really matter as long as it's from the center. Okay, I just did a 45-degree angle from the center. Now, from the side of the pin, I'm going to measure out in 5mm increments. I'll just do about 4 of them. I might need 5, I'm not sure. So look, 1, 2, 3, 4. And I'll do the exact same thing from the side of the bowling ball. So the exact same thing. 5, 10, 15, and it's just kind of gone off the sheet there slightly, but that's okay. And now all I'm going to do is I want the path of a locus of a point that is going to be equidistant both away from the pin as it is from the bowling ball. So from the center point of the pin, I'm going to swing an arc, and that extra 5mm, watch this, I'm going to swing an arc inside here, just like that, and I'm just using that distance here that I have here, but I'm just going to swing it inside here, and then I'm going to go down to the bowling ball, and the extra 5mm out from the bowling ball, which was this distance, I'm going to swing that arc to cut in there. Now technically, where the two arcs cross each other is a point that is both 5mm away from the pin and 5mm away from the bowling ball. Now I have to keep going in that sequence. So the next one now is going to be 10mm away and 10mm away. So swing an arc, back up to this guy, out to the 10, swing an arc. There's the next one. And then I only need 3 by the looks of it. Out to the third one. Swing an arc. And out to the third one here. And swing an arc. Okay. And it looks like that's all we need. And technically then, that is the locus or path of a point as it travels further away that is always equidistant away from both the sphere and the pin. So all I would do then is I would connect those up. Mightn't always be a straight line, okay? But what's helpful is where the path of that point passes through this line that connected out here, right there, it's very close to it, but it's right there. That's why it's important to have a good sharp pencil. Right in there, technically, is the center point of my cylinder. So now that I've found the center point, I also have the radius looking down it, because that's the distance from there to P. That's the radius. I should be able to draw in my, just going to fix the lead here, apologies guys, some compass. There we go. Now, putting my compass point here, pencil point onto P. I would always test it first. It looks pretty much bang on actually. And always work out as perfect as that. Okay. drawn it. So there we go. Okay, and there we have it. I have now found the center point of the cylinder, okay, and I've got the radius, because the center point, the radius would be from the center to P as the radius, okay, and P technically acts as the point of contact in relation to the pin and the cylinder, and if I was to join the center of this one, these two, the point of contact would be there, okay, and I could write in POC. Now, if I wanted to draw that in elevation, all I would do is I would extend up from the extreme right of the cylinder, the extreme left. Should be out there. And then the cylinder, if it was drawn in elevation, would look like this. And the extreme right line was out here. Now, they didn't ask us for this. I see nothing wrong with putting it in. Because when we look at a cylinder in elevation, we will see a rectangle. Okay, and there it is. That would be our little rectangle inside there as we look at it. Okay, so there's the second question done, guys. Not too bad if you have a good understanding, obviously, of solids in contact. So we're going to move on now to question A3, which is at the top right of the page. So just move this over and slide this up. So question number A3, and this is based on the topic of interpenetration of solids. Okay, so it says here, the image below shows a sign outside the offices of a company called Key Technologies. In the sign, a truncated copper pyramid is intersected by a triangular steel prism. So you can see here we've kind of got this copper pyramid and it's truncated. What they mean by that is that the top of the pyramid has been chopped off. Okay, and essentially what's happening also is that there's a triangular prism slicing through it. You can see it here. Okay, the drawing on the right below shows the elevation and incomplete plan of the solids which penetrate each other. So we've got the elevation here. The elevation is fully completed, but the plan view is incomplete and we have to find some of the details. Complete the plan showing all lines of interpenetration. It says here, and there's a little hint, use a section plane to find the crossover points on the edge DE. And you can see here that to give us the edge DE. And then it says determine the true shape of the triangle ABC. So we'll get onto the B part once we finish the A. So what we have to do is we essentially have to find, okay, I'm just going to come along with my marker here. We essentially have to find, okay, in the plan view, these kind of edges here. So you can see this one, okay, that kind of edge there, okay. There'd obviously be an edge running in underneath it, and then there'd be an edge running down at the opposite side. So that's technically taking care of this side. Up here, at this side of it, we're trying to find that kind of edge there, and there'll be another edge here, and that obviously runs down, and then maybe runs in, and so on. Okay, and we have to figure out those little details. A bit harder for me to kind of see it there, but you're getting the idea. So what we're going to do is, I'll start off by focusing on this side. Now what's helpful here, if we take the edge C, look, A, B, C. Now if I was to label those, A and B would be down here. So I'm just going to go A, comma, B. And then C is at the top. Now what's helpful just about that, technically, the AB, we can find where it intersects that face, because this face here, in the plan view, technically in the elevation, we see it as an edge view. Okay, so technically I can find the exact point where C is passing through it. Hits it right there. So technically, if I was to bring that down and extend C across, where it hits right there, that's where that point is. Right there, I've now found that point here in the plan. Okay, I need to now find where A and B kind of cut into the face, which is right here. So where that is, bring it down. And once again, I need to extend these guys out. So there's that one gone out, and that one. And it's simply a case then of connecting those up. So this guy will go down to here. This one to here. And what's helpful then is, I'm just going to heavy in this little bit of information here as well. Don't forget to heavy those edges in. You could lose a couple of marks. And then, normal orthographic, there is an edge running underneath it. That would be a line connecting there. So I would have to put in my hidden detail. So there's the hidden detail. And also going to just heavy in this line there, the whole way. There we go. Okay, so there is the right hand side of it completed. For the left hand side, it's a little bit trickier. It does say we're going to have to use a section plane to find the crossover points. There's multiple ways you can kind of go about this, depending how you learnt yourself. But based on the space that we have here on the sheet, it doesn't really kind of allow us to kind of maybe take an auxiliary view or anything like that. But section planes are actually the most appropriate way to take it, provided you know where to take them from. So what we're going to do is, you can see the edge DE here. Okay, if I was to label that, technically D and E would be this point here. So I'm going to do D, comma, E. So that would be D and E there. Now, what I want to do is I want to slice through the object, and imagine I'm cutting off the top of the triangular prism. So if I was to take a section view, a horizontal section, parallel with that line there at the top, which is where the DE is on, okay? So I'm going to take that horizontal section. So what I've done there is I'm after slicing along it, and it's like I'm after removing all this material here on the top of it. And what's helpful then is, technically, I've now got a point right here on the back face, okay, which is a triangular surface. Now, what I want to do with that is, I'm going to project that point down to my plan, and that gives me those two cut points on that surface there. The triangular face at the back, which we're seeing in the plan view here, it's going to give me one cut point right there, and the other one here. So there's my two cut points. Now, those two cut points will actually connect all the way to this point here at the front. Okay, have I found that yet? No, I haven't, so I have to project it down right there. Bring it down. It's somewhere along that line, and we know that line there is on the line C. So if I just extend C all the way along, lightly across. Okay, so that's gone lightly across. Technically, I've now found that point there where it goes through the building and then starts to emerge as it comes out the top of it again. I said building, I should say the truncated pyramid. So that point there now is a point on that horizontal section, and it connects to this point, and it connects to this point. So there's those 2 points. It's actually going to connect to them like this. There's one, and there's the other. Okay, and what's helpful then about that, I can heavy in this top line now. Just want to get that heavy then. Just start kind of making things a bit easier for me to see. And what's helpful about that is, on the edge DE, those two lines connected, I'm going to draw that down. That's going to show me where that point and that point is. Now, I'll heavy those in. And that one. There's that side of it. And that side. Okay, now I've found kind of the top bit where it starts to emerge out of it. I've kind of done that little triangle there. Okay, that is done. And now I have to obviously determine where this one connects down to here, like we did at this side. So it's the exact same process over here. So once again, this face now, okay, is now an edge view in the elevation. So from here, bring this down and then extend this line in. And extend this line in. And that then is going to go heavy as far as there. Do the exact same up here. And they will then connect here. So there's that side. And just make sure I've got the right lines. Okay. And likewise again, there's going to be an edge of hidden detail that I have to put in as well. That's running underneath it. So putting in my hidden details. Okay, there's my hidden details, and that is the part A of the question done. Okay, and you can see we used a smart sectional view there to kind of chop off the top of it, and it helped me locate points there. So that little triangle there, imagine that's what it actually would look like if all that had been removed. Okay, and by taking that sectional view, it helped me determine these 2 points here. Okay, so the next part of the question, determine the true shape of the triangle ABC. So the easiest way to see this true shape, okay, we could take an auxiliary, where I set up what would be known as an x1, y1 parallel, because when I look perpendicular to something, I can see the true shape of it. And we have an edge view of the surface ABC, which is the triangle here. I could set up an x1, y1 and project out A, B, and C, and I could take my distances from the XY line down. But there is probably an easier way based on the sheet, and all I'm going to do is I'm going to extend out my XY line out to there like that. And what I'm going to do is I'm actually going to roll back the surface down. So A and B are already on the ground, so technically that line there is a true length as we look down on top of it. So all I'm going to do is I'm going to rotate C around until it's sitting on the ground. So using AB as a hinge point, I'm going to rotate C, or bat it around until it's sitting on the ground. And now that C is on the ground, technically I would see that rotator, by bringing it down, I would see that rotator as a straight line going across horizontal. And it's like C has gone like this, up and down, and it's rotated until it's flat on the ground. So this is the new position of C. So basically C kind of went in this direction, and likewise here it went in this direction. So A now connects to C, and B connects to C. And what's helpful then is inside there, if I just use a little bit of colour, inside there, that is my true shape. Okay, I'm just going to write T, S. Okay, there's my true shape. So there, guys, is the third question based on the topic of interpenetration. Now we're going to move on to the fourth question, A4 at the bottom of the page. So this question here is kind of based on skew lines or intersecting lines. Okay, and a little bit of understanding in the start of the question. It says here, lasers are often used in CSI, crime scene investigation, so the TV show, to determine the trajectory, so the flight path or the path of a kind of like a bullet. Okay. In the drawing on the right, two bullet paths are represented by the lines A, B, and CD. So this is the path of a bullet A, B in elevation, and this is A, B in plan, CD in elevation, and CD in plan. Using geometric constructions, determine if the bullets were fired from the same location. So did they come from the exact same point, but maybe just faced in a little different direction? Okay, is basically what they're asking here. Okay, and we can then determine if these are skew lines or intersecting lines. Okay, if they came from the same location, they'll be intersecting lines. If they didn't come from the same location, then they will be skew lines. So the only way I can actually test for that, it's easy enough, is if I extend AB in elevation and then extend CD in elevation until they intersect with each other, and they intersect right there. Now, I say intersect, they cross paths right there. Now technically, in plan, if I extend this one and this one as well, A, B, and CD, technically, if they are intersecting lines and they come from the exact same point, then it should be directly below this. Okay, so the same thing, I'm going to extend those as well. And just making sure I have the right line here now, without getting my head in the way of the camera. And it looks close enough. Now, technically, they should be in line with each other. Actually, I was thinking for a second they look close enough. So, there's my 2 points. There was the one in plan, there was the one in elevation. So if you bring the one from elevation down, you can see here that they're not meeting up. Therefore, I've determined, or I've deduced, that these are in fact skew lines. So I'm going to put in a little tick in there. Okay, so they are skew lines. They do not come from the exact same location. Okay, so the bullets are fired from different locations. In plan view, it comes from this location, whereas in the elevation, it's up here. Okay, so they are skew lines, not intersecting lines. Now, part B of the question, draw a line joining points A and C. Okay, so we want to draw a line joining points A and C and determine the true length of that line. Okay, this is just using the principle of a cone. So I'm going to connect A and C in my plan view. Put it in heavy. Now, what I can do is I can use the principle of a cone to kind of work this out. If you imagine we're looking at a cone upside down, okay, I'm going to take C as the point because I'm going to rotate it this way. If we were to do a cone, okay, and C is here, and technically A will be around here. I've probably done that. Yeah, I've done it close enough. So there's A. Okay, that line on the cone is what's known as a generator. Okay, but technically when I look down on top of the cone, I'm going to see a circle. Now what I want to do is I want to rotate A until it's to the extreme left of it, and then when I look at the left of it, I'm going to see A, it's gone rotated around until it's gone into this position. That technically is the new position of A, and when I look at A out here and I'm looking perpendicular to it, I will then see the line from C to A as a true length because that will be on the extreme generator. So to do that in my plan view, all I'm going to do is I'm going to use C as the center point. Because that is the apex of the cone. I'm going to rotate A until it is technically C now to A. A has rotated around until it's in its new position here. Right there, I'm going to call that A1. Doesn't really matter what you call it. And I've rotated, and remember in elevation we're always looking perpendicular to the XY line. So now I can see the distance from C to A. That is now technically going to be a true length when I look at it in elevation. So all I'm going to do now is I have to find the new position of A. So A is now not here anymore. It's actually going to be out here. And as I rotate, all that's going to happen, and that appears in elevation, is that's going to be like a straight line. Because when I look at the triangle, technically in elevation I would see this, in plan view I would see this. So A has moved from here out. That's essentially what's after happening. So A has moved from here out to here. That there now is A1. And here is, if I connect C to that, okay, that is my true length from A to C. That is the true length line. This line here, that one originally was not the true length, as was this one. This is now the true length line. Okay, so there you have it, guys. That there is the fourth question. A little bit of understanding in that one. Quite easy if you knew what to do. You can see there wasn't too much work in it, but the understanding behind it was, I suppose, where they were really testing you there. So just going to zoom out there now, guys, and move that back up to the center of our screen. So there you have it, guys. That there was the 4 questions completed from the 2013 exam paper. This one, more than manageable. This one also, students possibly might have found, because they often don't like to do the solids and contact questions. It's easy enough one if you understand what you're doing, okay? And this one was easy enough, once again, if you understood what you're doing, but these are probably the ones I think maybe students would have found the most difficult. But look, guys, that there is the 2013 exam done from the section A. I hope you found that helpful. Okay.